Hello, welcome to this lecture. This is seventh lecture of this current module on multivariate random variables, and so far we have discussed their several properties, and in the last lecture that we are supposed to cover in this lecture is that moment generating function. So we will complete that part, and after that we will discuss something about their different distributions. So multiple random variable, when we talk, it is their joint PDF and joint CDF, and if it is discrete then it is joint PMF, that you know. So these things we will be discussing, and after that we will give some standard example of bivariate case. Means mostly you know that when we are discussing different properties, we are discussing in case of the bivariate random variable where there are two random variables are involved. And after that we will also take you through the concept how it can be extended for the multivariate random variable cases where more than two random variables are there. So today's lecture we will start with the discussion of this moment generating function, and this moment generating function we have discussed earlier in case of the single random variable. And as this module is on this multiple random variable, we will discuss this one first in case of this multiple random variable, and after that we will take different distributions as well. So outline of our today's lecture is first the moment generating function of multiple random variable. We will know that how in case of first of all, in case of two random variables, how we can generate that moment generating function, and after generating after obtaining its MGF, that is moment generating function, we will know that their utility, that if we take that that rth order derivative. Now when we are talking about the rth order derivative, that is in the context of the single random variable that we have discussed earlier, but here as there are more than one random variable, so there will be so derivative order also may change for the different random variables, and after getting that that derivative, if we evaluate that function at the origin, then we will get that moment. That also we will discuss, because that is the main focus of this of obtaining this moment generating function. So we will get different moments, and for the multiple random variables, when we are talking about the moments, then also there is a sense of joint moment, that is for the, if it is bivariate case, then it is for the both random variables, the order for the different order for the different random variables, we will come to know what are their moments. So that is the reason why we will learn about this moment generating function. So after that we will discuss about this bivariate probability distribution functions, and so far as this joint distribution is concerned, there are not many examples. So there are two things, those are important, is this or frequently used is this the bivariate normal distribution, and second one is bivariate exponential distribution. This bivariate exponential distribution we have discussed while in this module itself in previous lectures. So here we will just once again we will mention it just to complete this one. So these are the two bivariate joint PDF, and that probability function, probability density function is available. So these are also of many use in different fields, including civil engineering. But here one thing is important that I also mentioned earlier, that getting a joint distribution from there from the marginal distribution is not easy. And for example, this bivariate normal distribution case also, it is not that if I get some marginal distribution, we cannot create what is their joint distribution. Opposite side is true. Opposite side means that if both the random variables are jointly Gaussian distribution, then we can say that their marginals are also Gaussian, but the reverse is not true. That also we will discuss. So what the major part is will be untouched so far is that how to get the joint distribution. because these are the only two joint distribution form is available. So, there that the recent technique on copula that we will be taking up towards the end of this module that I mentioned earlier. So far whatever is existing apart from the copula we will discuss, and these two are the bivariate normal distribution and the bivariate exponential distribution. This we will include in today's lecture. And after that, the properties that we are discussing for the case of the bivariate, we will take the same concept for the more than two, particularly when we meant that multivariate. So, more than two random variable case, we will extend the same concept. So, to start with that joint moment generating function, similar to the moment generating function of a random variable defined in the previous module, the moment generating function of two random variables is again there are two cases, one is the discrete and another one is that continuous random variable case. So, in case of the discrete, we have discussed for the single random variable, and here if there are two random variable involved, then say that x and y. So, for this both this random variable, the moment generating function is the expectation of the function of that exponential tx plus uy. So, so if we take this expectation of this function, now in the earlier lecture we have discussed for a function how to get that that expectation of a function. So, that this is nothing but this function multiplied by their probability mass function, and we have to sum it over for all x and for all y. So, if we do this one, the function that we will get that is the moment generating function of the joint PMF of joint PMF between x and y. Similarly, in case of the continuous random variables, if this x and y two random variables which are continuous, then the it is also that expectation of this of the exponential function, which is exponential of tx plus uy, and to get this exponential we have to do the integration over the entire range of both the random variables. Here this it is integrated from the minus over the entire real line minus infinity to plus infinity, this function exponential of tx plus uy multiplied by their joint PDF f xy and it is integrated over the entire range. So, this one will get that moment generating function for the continuous random variable. Now, just if we want to know their marginals, now what we have done, that this is just the power that we have used, the power of this x and power of the y. So, which are here both the cases is 1. Now, if we want to know for the marginal, and we know that how to get that moment generating function of their marginals. So, the marginals means that we discussed earlier is that the distribution of one random variable irrespective of the distribution of the other one. So, this moment generating function of the x, if I know, then we know that this is the will be the expectation of the exponential tx only. So, now that exponential of tx means here the uy, the term was here, just it is the y power 0. So, this component will not be there, not y power 0. So, this component will not be there. So, that u we can say it to be 0. So, not that y power 0, it is u equals to 0. So, now if we put that u equals to 0, then we can write that the moment generating function of the joint random variable x and y, there we have to put that t, and for in place of the u we have to put the 0. So, this is what we are explaining is that, so how to get the moment generating function for the marginals, that is if we know the moment generating function of the joint random variable, then by replacing the suitable attribute we can get the moment generating function for the marginals. Similarly, for the y also we have to replace that t by 0 and we have to keep this u in from the joint moment generating function. Now, this is also again we have discussed earlier that in case that x and y are statistically independent, then so far as the moment generating function is concerned, then we can write that this moment generating function of this joint moment generating function should be the product of their moment generating function of the marginal of the random variable involved. So, this mxt is nothing but the moment generating function of x, and myu is the moment generating function of the y. So, both are from their marginals, and if we multiply it, and if this product is equal to their joint marginal joint moment generating function, then we can conclude that this then this x and y are statistically independent. Now, for this multiple random variable, just we have to just simply extend the idea that we have seen, is that in case of if there are k random variables, then this for the joint moment generating function between that x1, x2 and up to xk, then what we have to take is that there are different, these are all means attribute that we are considering. So, this will be the expectation of a function which should be the that exponential of that t1 x1 plus t2 x2 plus t3 x3 up to tk xk. So, basically from this, now if we just see that this is the for the single random variable, this is the exponential of tx. Now, for the two random variables, we are just adding that that exponentials are taken for this tx plus uy. Now, if there are another random variable that we have to add with some other attribute. Similarly, for this k numbers of random variables is explained here, you have to take the exponential of this function, that is ti xi, I varies from 1 to k. Now, after we get this joint moment generating function, what we generally get, what is our interest, that we have seen in case of the single random variable also, that we have to take some particular order of their derivative, and we have to evaluate its value at the origin to get that order moment. Okay. So, so here also for the multiple random variable also we have to get the suitable derivative with respect to the different random variable involved, and we have to evaluate that one at the origin to get their moment for that order. Now, we will discuss it in general form first, that if we are talking about the rth moment of the xi. Now, this xi is what we are talking about, whatever the random variable involved, say there are some k random variables are there. So, any one if I want to know, and I want to know what is its rth moment, then what we have to do is that we have to differentiate the joint moment generating function r times with respect to that ti, and then evaluating the derivative with ti is equals to 0. So, the expectation of this ith variable, ith random variable which is involved here, power r. So, this moment will be the rth order moment, this one is the derivative is the rth order derivative with respect to that ti, which one is taken. So, it is written at the beginning, so which is the x1, but it is not necessarily that it has to be put here. So, any random variable between this x1 to xk, I think the better explanation, you know, that it will be the x1, x2, then xi somewhere in between, where I is I can take any value between 1 and k. So, and with respect, so the, and it should be derivative should be taken with respect to the corresponding attribute, that is a ti here, and after getting this derivative we have to evaluate this value of this function at ti equals to 0. So, this is the general expression, and it is not only for a single random variable, we can do it for even for this any subset of this random variable. So, just I want to know that the expectation of x1, x2, say for example, out of this k random variables, I just want to pick up x1 and x2. So, I have to take the that dou to this moment generating function with respect to that dou t1, dou t2. So that 2 times derivative, first time I am doing with respect to the t1 and then with respect to the t2, and after getting this derivative we have to evaluate it at t1 equals to 0 and t2 equals to 0. So this is what we are explaining even in this general case where there are, say that 2 random variables are there, the mixed moments. So here the mixed moments means we even can change the order, so that there are 2 random variables, that xi and xj, and for the xi the order is the r and xj the order is the s, can be generated from the joint moment generating function by differentiating r times with respect to the ti, because it is xi. So r times with respect to the ti and s times with respect to the tj, because this is xj power this s. So s times with respect to tj, and then evaluating the derivative with ti equals to tj equals to 0. So this is what is explained here in case that there are 2 random variables. So we have to doing this derivative with respect to the r times with respect to the ti and s times with respect to the tj, and then we are evaluating that function at ti equals to 0 and tj equals to 0. So where will this be useful is that now once we get this expression, then I can vary any value of this r, whether if I need that expectation of x, then I have to put that r equals to 1 and s equals to 0. If I want that their expectation of x y, then I have to put r equals to 1, s equals to 1, or other way, if I want that second moment of y, then I have to put that r equals to 0 and s equals to 2. So this general expression can be used whatever way we want to know. So here one example we have taken, and this example again also taken very carefully because the properties of this distribution we already know, we have seen. Now what we are looking for through this problem is that the reason for this taking up this type of problem is that we know what is this PDF, and in fact just by reading the problem itself we should know that what the answer is expected. But whatever the theory we have discussed with respect to this moment generating function, or specifically the joint moment generating function, then we will again apply that one to cross check that whether what our belief is, whether this is being satisfied through this problem or not, that we will see. So the problem states here that this is a life of a structure, and this structure, the life of that structure depends on the various components. Here it is simplified with respect to the 2 components only. So just to take this for the discussion problem. So this life of a structure consists of 2 subcomponents, depends on their individual lifetime, say x and y. So what our target is that I have to model the life of a structure, that structure having 2 subcomponents, and the 2 subcomponents having their lifetime, both the lifetime of both the subcomponents are 1 random variable each. So for the first component, say the random variable denoted for the x for its lifetime, and for the second component the lifetime is denoted for its for a random as a random variable y. And both these one are exponentially distributed, and their joint density function of this x and y is given as this f x y is equals to 2 exponential minus x minus 2 y, where x and y is greater than or equal to 0. Determine the joint moment generating function of x and y, and then compute the mean of x and y, also compute the covariance between them. Now before I proceed to solve this problem, why this problem has been taken, that I mentioned just minutes before, is that this function we know, and it can be easily shown that both this x and y are independent, and their joint function is nothing but the product of their individual marginals, and marginal for the x is e power minus x, and marginal for the y is 2 e power minus 2 y. Now this type of problem we have taken up earlier, so I am not going to how to prove that one, that I am not taking at this level, because you can just see few lecture previous where we have solved this type of problem. So, with this one, that what we know is that both this x and y are independent. So, if we know, then the covariance between them obviously will be 0. That also we discussed earlier. Now, also what we discussed, the exponential distribution. So, e power minus x is one exponential distribution for which is the marginal distribution for the x, and this the lambda parameter is here 1, and for the y the marginal distribution is 2 e power minus 2y, where the lambda parameter is 2. So, that exponential distribution also we know, and we also know that the mean of an exponential distribution is 1 by lambda. Okay. So, if we know that one, then the mean of this x will be 1 by 1, that means 1, and mean of the y will be 1 by 2, so half. Now, these things, these things what we will do now for this problem is that first of all we will determine the joint moment generating function, and as we know the answer already, we will just cross check with it that whether the how we can use this moment generating function to get their respective moments. So, once this answer we can check, and then for the any other moment for this joint distribution we can use the same methodology to get that whatever the order of the moment that we need. Okay. So, we will just now now we will go for this solution, and first what we have to get, that we have to get its moment generating function. So, just now what we discuss is this moment generating function is the for the two random variables x and y is the expectation of a function which is exponential of tx plus uy. Now, this one we can express that e power tx plus uy multiplied by its joint density, and it should be integrated over the entire support of the random variable. Here both the random variables are taking the non-negative range. So, it is from 0 to infinity and 0 to infinity. So, both this x and y. Now, this joint density we know that is 2 exponential minus x minus 2 y, and then multiplied with this e power t x u y. So, so this t and u are the variables through which this moment generating function will be expressed. Now, after doing some algebraic steps and doing this integration, we will get this expression putting the suitable limits of course, and we will get that it is 2 by t minus 1 multiplied by u minus 2. So, this is what is shown as to be the moment generating function for the PDF that we took. Now, our next step is to get their mean of x, mean of y, and its covariance. Now, to get the mean of x, what we have to take is that we have to take that expectation of x, and just now we have shown the step how to get the mean of their marginal distribution, that is we have to put the suitable order. So, here it is very specifically mentioned that how we are putting the order. So, expectation of x, when we are talking about, we are putting that the order of this derivative should be for the u, for the t it should be 1, and for the u it should be 0. So, the basically we are doing a first order derivative with respect to u, sorry, this will be t. So, with respect to t, because t is here for this x. So, first order derivative of this moment generating function with respect to t, this is wrong, this is t. So, here you can see that dt power 1 and du power 0. So, this is dt. Now, if we do this one, and at the end what we have to do, we have to put that t equals to 0 equals to 0, and if we put this one with this expression, then we are getting it to be 1. Now, you can see that marginal distribution of the x was an exponential distribution, we have seen that one, and that is e power minus x, where that means the lambda equals to 1. So, mean is 1 by lambda, that is 1 by 1, which is 1. So, from the moment generating function also we are getting that its mean of the random variable x is 1. So, now we will get what is the mean of this x, and we know that before I go to the next slide, we know that mean should be equals to 2. So, how we are putting this one, again following the same procedure, that is here we are putting that t equals to 0 and u equals to 1. So, this is again the first order derivative with respect to u. So, again this is just swap between. So, this would be u. So here you can see it from here that this would be u. So we are doing the first order derivative of the moment generating function with respect to u, and after doing so, what we are getting is the value at t equals to 0, u equals to 0, and we are getting the value to be half. So which is again as per our experience that if the marginal density is 2 e power minus 2x, that is it is an exponential distribution with lambda parameter 2, and its mean should be 1 by lambda, which is equals to 1 by 2. So this is what is there. Now what we have to do, we have to calculate its covariance, and you know the covariance. To get the covariance, first of all we have to get that expectation of the joint moment, that is covariance is equal, covariance between x and y is equals to expectation xy minus expectation of x multiplied by expectation of y. So that expression we know, and so if we know that expression, so we have to first get this quantity xy, and this one we have done it earlier with respect to the PDF. In fact, all these things, that expectation of x, expectation of y, expectation of xy, we did it with the help of the PDF. But here what we are doing, we are showing that how we can use the moment generating functions. So here that expectation of x y, that means here the both that r, that notation that we used minutes before, the r equals to 1 and s equals to 1. So this is that second order derivative with respect to dt and du both. So this is that expression, that is the derivative of this moment generating function with respect to t as well as with respect to u. So this will be d2, sorry, this will be d2 here. So 1 plus 1 you can see here, this will be d2. So if we do this derivative, and we will get this this expression, and again we will be evaluate this function at t equals to 0 and u equals to 0, which will yield the results to be half. So expectation of xy is equals to half. Now the second one, we already know that what is expectation of x and what is expectation of y. Now the covariance is just this minus product of those. So the covariance is the expectation of xy minus expectation of x into expectation of y. We just simply put whatever we got, and we can see that this covariance is 0. Now covariance is 0, as I mentioned earlier also, again I am mentioning here that the covariance 0 does not mean that random variables are independent, but opposite is true. If the random variables are independent, covariance is 0. So we started this problem, we knew that these two random variables x and y are independent. So the expected, or the what we should get, and I cannot use the word expected because this is a statistical word that we are discussing now. So we knew that covariance will come 0, and that is what we have seen when we are getting those estimates from the moment generating function directly. Well, so next we will take up two bivariate standard distribution which is there, and in fact that bivariate exponential distribution that we are going to discuss now, we have used this one earlier also. And in case of this bivariate joint distribution, we are having only two random variables. If not only two, there may be, but these are the two things that is mostly you use, that bivariate exponential distribution, and next is the bivariate normal distribution. This we will discuss a little, and afterwards we will go for this multivariate one, and again we will come back to this how to get the joint distribution from the marginal through copula later. So now the bivariate exponential distribution, this is a PDF and CDF of this bivariate exponential distribution is expressed like this, that this is the PDF, you know, that f x y, xy is equals to that u plus wy multiplied by v plus wx multiplied by exponential of minus ux minus vy minus wxy. And if we do their if we want to know their CDF, that is cumulative distribution function, then this is equals to 1 minus e power minus ux minus minus exponential minus vy plus exponential minus ux minus vy minus wxy. Now, range for this x and y are the random variables for which the range is greater than or equal to 0. So, it cannot take the negative values. The support for this distribution is from 0 to infinity. The parameters, there are 3 parameters you can see, one is the u, v, and other one is w. So, this u and v is straightforward, which is the non-negative parameter is greater than 0. So far as the w is concerned, it is having a, it is limited by 2 things. One is that it should be greater than or equal to 0, and other one is that it should be lower than this u v. We took this problem earlier just to know that what is the possible range of this third parameter w. Now you can see here, if the w can take from the 0 to u v. So upper limit we have seen, the lower limit. Now if the w is equals to 0, then this component will not be there. So that case, basically when we take the 2 random variables x and y are independent, then this component cancels out. So that just now we have seen. So this w parameter is basically taking care of there if there is any means if there is any dependence between x and y, that is being taken care through this w. So we have discussed this problem just now also and earlier also, and we have seen their parameters earlier. So this is one example of this bivariate distribution, which is exponential, and other one is this bivariate normal distribution. This is having in many fields we use this whenever, basically even earlier, that whenever we are talking about this joint distribution, we generally go for this bivariate normal distribution, because this, it is grounded on the firm theoretical basis, and to get for the other distribution, other joint distribution is not that easy. And so we have found earlier there is a tremendous application of this bivariate normal distribution in many research fields, including civil engineering. So this bivariate normal distribution, when we are talking, this is then an example of the joint density function of 2 continuous random variables, say that x and y. And in such cases, the marginal density function of both the random variables are also normal distribution. So you remember that first we are stating this, and after that we are stating this statement. That is, first it is if their joint density function is Gaussian, means Gaussian or normal distribution, then we can say that their marginals are also normal distribution. However, reverse is not true. That is, if both x and y are normally distributed, their joint distribution not necessarily be joint normal distribution. So this not necessarily be joint normal distribution means that the reverse is not true. What we have also mentioned this point earlier as well. Now how this PDF is can be expressed as like this. So there are basically 5 parameters for this one. You know, for a normal distribution, there are 2 parameters. One is that its mean, and another one is that variance. So here there are 2 random variables are there. So that for one random variable, this will be the mean of one random variable, variance of that random variable, and mean and variance of the other random variable, and their joint dependence. So there are total 5 parameters will be there. And these 5 parameters are here. You can see that this that sigma x is the standard deviation for the x, sigma y is the standard deviation of the y. This rho is the correlation coefficient that we discussed earlier. So this rho is the correlation coefficient between x and y. Then this mu x is the mean of this random variable x, and this mu y is the mean of the random variable y. Now just to read out this one is that 1 by 2 pi sigma x sigma y square root of 1 minus rho square exponential of, there are 3 parameters, there are 3 parts of this, what is there inside this exponential. So first one, so this is taken common, that is minus half by this 1 minus rho square. After this is multiplied with the 3 different parts. The first one is this x minus mu x by sigma x whole square. Now you can see here this is written in such a way that you can see now this is also can be taken to the reduced random variable, that is transformed, that is x minus mu x by sigma x. So this is why how it is written. Just in a minute we will take up that one. So this is x minus mu x by sigma x whole square, and the third component is the y minus mu y by sigma y whole square, and the second component is their joint again, that is 2 rho x minus mu x by sigma x multiplied by y minus mu x by sigma y. Now you can see here itself that if they are independent, that is if the x and y are independent, then you know that this will be the product of their marginals. So that is the check for this independence. So if they are independent, then you know the covariance will be 0. Then if the covariance is 0, then correlation coefficient is also will be 0. Now you put that correlation coefficient, that is rho equals to 0 here, then you can easily separate out two distribution, which are the first one will be the normal distribution for x, and other one will be the normal distribution for y. So this you can say. So this rho is basically taking care of if there is any dependence between x and y, and also you know that x and y are the support is from the minus infinity to the plus infinity. So whatever I told it is written here, that is mu x is the mean of x, mu y is the mean of y, sigma x square is the variance of x, sigma y square is the variance of y, rho is the correlation coefficient between x and y. Now just what I was talking, that if we just replace this one, that replace means that if I put that another random variable z1, which is the x1 minus mu x by sigma x, and z2 is the y minus mu y by sigma y, the PDF for bivariate standard normal distribution. So earlier we have seen that after this transformation we are getting the standard normal distribution, here also we are getting, but that is again the bivariate. So this bivariate standard normal distribution, if we want to know, then for this expression we have to put that z1. So this then their PDF, joint PDF will be 1 by 2 pi square root 1 minus rho square exponential of minus z1 square minus 2 rho z1 z2 plus z2 square divided by 2 into 1 minus rho square, for which again this z1 z2 are also not from minus infinity to plus infinity, this is from 0 to 1, this is from 0 to 1. This is an example just to view that how the joint distribution is the joint distribution looks like. Here we have taken one example of this joint normal distribution. You can see that now this is kind of surface, and there is a three-dimensional surface, and the volume below this surface, that is a three-dimensional volume, and that volume, if we just extend the idea of this, that what we have discussed for the single random variable, that that area below the curve for a single random variable is equals to 1. Now here in case of the joint, if I take the bivariate case, because there is the pictorial representation is possible only up to the bivariate case, because x and y. So this is a kind of surface, and there is a volume is there between the xy plane and that surface. So what we are talking, if we refer to this figure, is that this is your x axis, this is your y axis. So this is your xy plane. So the volume in between this surface and that xy plane should be equals to 1, just to satisfy what is the requirement for a PDF. That is the total volume that is between that is covered by this surface is equals to 1. So volume enclosed by the surface of the bivariate normal PDF is unity. This one is shown here. Now this one we will just express it in a similar way, just after doing some algebraic manipulation. Just we will see that why we need this one. So the same expression. So this expression that I am going to tell you now and the joint distribution, that is between the x and y, are same. What we are doing is that we are trying to separate out what is the marginal distribution of x. So marginal distribution of x, which is having the mean mu x and variance sigma x square, then we know that what is this distribution by this time. So if we just want to take out that component out, what is remaining? That is what can be done in few steps, and this is what is done. So first of all, what we are writing is this 1 by square root of 2 pi sigma x exponential half x minus mu x by sigma x square. So this is nothing but the marginal distribution of x. Now this quantity is taken out, and what is remaining we are just expressing it here. That's 1 by square root 2 pi sigma y square root of 1 minus rho square. So you can see that this is the outside constant, and this is another constant. If we multiply these two, it is coming that 2 pi sigma x sigma y square root 1 minus rho square. So similarly in that way, so whatever was the inside, we have taken this one out. So what is remaining is noted here. Why this is important, why you are explaining this, why you are expressing this the same expression in a different way, is just to know there what is the conditional distribution. And you know that we have discussed for the bivariate case, the conditional distribution is expressed, and this has to be just divided by their marginal densities. So that is why the marginal density is taken out. And if I just want to know what is the conditional density function for this x given y equals to this, so this f y given x is equals to, so this will be the joint density divided by the marginal density of x. So now you can see that this is just swap, this is wrong. So this will be the conditional density function of y given x equals to x. So this is what is expressed here also. So this, the conditional distribution of y given x is that the joint density divided by the marginal density of x. Now what we will get? So this is the marginal density of the x. So this has to be taken out. So what is remaining here is nothing but the conditional density of y given x. So this is what is explained here. Now what you can see here is that this is also taking the form of a normal distribution as well. How it is taking the form? Because you can see that this is square root of 2 pi sigma y, this one. So this full component, that is the standard deviation, that is sigma y multiplied by square root of 1 minus rho square is the standard deviation of the conditional distribution of y given x. Similarly, exponential half y minus this full quantity is the mean of the conditional distribution of y given x. So the unconditional mean of y is mu y. Now and the conditional mean is mu y minus rho multiplied by sigma y by sigma x multiplied by x minus mu x. So you can see that the conditional mean is changing with respect to that, it is dependent on the value of the x, it is here. And similarly sigma y 1 minus rho square, which is the standard deviation of that conditional distribution. Marginal density function of x, yes, so this is the marginal density function of the x, which we have divided it by to get this conditional density. How to get the conditional density, that we discussed earlier? You can recall that f y given x is equals to f x y divided by f x, that is that joint divided by the marginal. So this marginal was divided by to get this conditional. And so once again we will just see what is their conditional mean and conditional variance. So this conditional mean is this, that is conditional mean of this y given x equals to x is equals to mu y plus rho multiplied by sigma y by sigma x multiplied by x minus mu x, just what we have seen it from this expression. This expression is also that Gaussian distribution, that is normal distribution, and from this normal distribution form we can say that this component is the mean of that conditional distribution, which is basically we are taking this minus common, that is why this sign becomes plus. So this mu y plus rho sigma y by sigma x multiplied by x minus mu x, this is the conditional mean which is shown here, and the conditional variance is the sigma y square 1 minus rho square. Variance we are talking about because this is the standard deviation. So this conditional variance is sigma y square 1 minus rho square. Now, as when we started this lecture, that we will take some of this bivariate concept to this multivariate one. The concept can be easily extended. So, we will discuss about that one with the context of this multivariate random variables having more than 2 random variables. Basically, we will try to generalize it in terms of the n random variables involved. So, so far we have discussed with the 2 random variables and their distribution function, their different properties and etc. we have discussed. We have taken up some problems also, but in many real cases we are interested in more than 2 random variables representing different quantities of interest from the same experiment and the same sample space. So, in civil engineering particularly, because we are talking in respect to that, if we see that, suppose that in the transportation engineering there is a junction of the road network where there are several roads are approaching to that, so that the number of vehicles that is approaching towards that junction may be of interest, and there could be the more than 2 roads that is meeting at that point. So, what is the behavior, what is the volume, or what is the total traffic volume at the junction? If we want to know, then this kind of analysis is there where the number of random variables involved will be more. Similarly, the different source of the fresh water is joining to a reservoir, is draining to a reservoir. So, if we just want to know their joint behavior, there also this kind of application can be found out. So, now to do this one, the concept that we have discussed for this bivariate case can be extended for the multivariate random variables as well, having more than 2 random variables. So, now discuss these things in the context of the general framework, that is the n dimensional discrete random variables. If we want to discuss first, so this is n dimensional, means there are n random variables. The n tuple cases are we have to consider jointly, and these are the discrete random variable. In case of the discrete random variable we are discussing. So, if x1, x2 up to xn are the random variables defined on the same probability space, then x1, x2 up to xn is defined as an n dimensional discrete random variable if it can take values only at a countable number of points x1, x2 up to xn. These variables x1, x2, xn are said to be the joint discrete random variables. Basically, means what we discussed earlier is that for the 2 dimensional case, just take x1 and x2, there are 2 axes orthogonal to each other, and take some points. So, it can take only few points on that plane made by 2 axes x1 and x2. Now, just extend this one to this n dimensional space where there are n axes which are the x1, x2 up to xn, and take some point which point should be denoted by the n coordinates. Now, n coordinates means x1 equals to this, x2 equals to this, x3 equals to this, like this up to xn equals to this. Now, those specific points are consist that probability space. So, if I take the full, I should not say even volume, because volume is again the 3 dimensional. It can go even more than 3 dimensional. So, for those specific cases, if the probability mass is concentrated, then that is known as to be that multivariate joint discrete random variables. Now, to know that what is their probability involved is this one. So, that the joint PMF, because you know this is discrete, so we have to discuss this one with respect to the PMF, probability mass function of that n dimensional random variable, that is x1, x2 up to xn, is defined as the intersection probabilities of the n sequence of the event. So, this n sequence of the event is this, that is if x1 equals to x1, that is, now you can know that these are the this is the random variable, this is the specific value of the random variable. So, this x1 takes the specific value x1, x2 takes the specific value x2, and up to like this up to the xn takes the specific value xn. So, for this joint case, means all these things are occurring together. So, this is that if that x1, x2, xn are the points in the n dimensional sample space of this variable. So, that probability is taken only for those specific points, otherwise it is 0, then that is the joint PMF between this, between the random variables x1, x2, xn. And this is what is shown here, that is that the probability mass function is defined as that for this x1, x2, xn is the probability of the joint occurrence of all these events, and these are belongs to that that probability space. This outcome, the specific outcome, joint outcome, is belongs to that that sample space. Now, properties again is extending the same idea, that it should be the total. If I take this each and every points, if I take what is that probability, so that probability should be greater than or equal to 0. So it should not be the negative number. Again, if I just sum up for the all the probability masses for all those feasible points, then it should be equals to 1. These are the two basic criteria to satisfy the condition for to be a valid PMF, that we have discussed earlier for the single random variable, for the bivariate random variable, and now here it is for this multivariate for the n number of cases. Keeping the basic concept same, these are the two properties to satisfy the condition of a PMF. And the cumulative distribution function is that you know that cumulative distribution function here, just I will just take a minute, that all these attributes now I have taken for this x, x1, x, x2, x, xn, x. Why I have taken, I will just explain in a minute. This could have again, this could have been also that different attributes, that is for x1 it is x1, for x2 it is x2, that also it can be done. But just to show here, in this case, if we are talking about only a single point of in that probability space, then it is a summation of all the feasible points, those are below this specific number x, that is x1 less than equals to x, x2 less than equals to x, up to this one, that xn less than equals to x. So, if I sum up this one, then I will get the cumulative distribution function for that joint PMF in case of the n random variables involved in that multivariate random variable case. Now, for the same is, if I take for this continuous random variables also, if this x1, x2, xn are the continuous random variables, that is similar to this discrete random variable, if these are the n random variables defined on the same probability space, then x1, x2, xn is a n dimensional continuous random variable if and only if there exists a function such that, these are the two conditions, again you know that for the function should be for all for the entire range of this random variables should be a non-negative number, should be greater than or equal to 0, and their integration over the entire range of each random variable should be equals to 1, and you know that this should be n. So, dx1 up to, in this way, up to dxn. So, n numbers of this integration in this n different directions of this random variable. So, dx1, dx2 up to this, up to it is dxn. So, these are the two conditions that should be satisfied. Then joint CDF again, if we are talking about, then here we have just taken as that is in even more general case. For the discrete case also that can be the general case, but I have discussed it in a specific condition. So, here what we are taking, that the x1 is the specific value up to this x1, and like this, if we want to know what is the cumulative what is joint cumulative distribution function, is the probability of the x1 from minus infinity to x1 intersection x2 from minus infinity to x2, like this up to xn from the minus infinity to that xn. So, if we take this joint occurrence, this intersection means you know there is a joint occurrence of all these events, then this one you know that we will get it from this integration, that is from minus infinity to x1 for this dx1, this here, that is the variable is replaced as alpha 1. So, it is d alpha 1 like this, the n times integration up to this d n, and this can go in this way to get this joint CDF for this joint multivariate case. One quick example we will take, and this is that involve the 4 random variables I, j, k and l, and this is a PDF is defined by, and we have to calculate the probability of I less than half, j less than 3/4 and l greater than half. So, there is no for k it is not defined anything. So, just this is you can. So, here now one thing that we have not shown here, you can check yourself that whether this is a valid PDF or not. Now, to check whether this is a valid PDF or not, you have to do that integration for their range between 0 and 1 for all the random variables. 4 times integration you have to do, and you have to put their integration limit and check whether the final is coming to be 1 or not. So, here what we are trying to look at that for this specific space, what is the probability? Simply we have to do the integration for the specific range. For this one, you know that for this half for the j, it is the range is the from half to 1, and for the I it is the half to 1, for j this is 0 to 1, for this k it is for this I it is 0 to half, for this j this is 0 to 2/3, for k it is the entire range 0 to 1, and for the l it is half to 1, because you can see that then it is satisfying these limits. So, the inner one, the first integration is for this I, limit for the I, which is less than half, and the lower range always is 0. So, it is 0 to half for the I. Similarly, we have defined these integration limits. This is the PDF, and we are doing this integration to after doing this integration, we will gradually get what is their joint what is the joint probability is 27/64. So, in this lecture we have discussed about their joint moment generating function for multiple random variables. Then we have taken the 2 standard bivariate joint PDF and CDF, bivariate exponential distribution and bivariate normal distribution. After that, we have taken the multivariate cases, and we have discussed one problem as well. In the next lecture we will discuss some more these properties, and we will also discuss about the functions of the multivariate random variable case, and after that we will again discuss about this multivariate case to get their joint PDF from the marginal one using copula. Thank you.